All right, so we're now ready to introduce Markov decision processes. And Markov decision processes form essentially the foundation of reinforcement learning. So we need some tools to be able to analyze the properties of the algorithms that we're going to design for reinforcement learning. And it's through the lens of Markov decision processes that we're going to make this formal. Okay, so again, we just talked about stochastic processes. In particular, we focus on the idea that we make some assumptions to allow our process to be Markovian, and this is the picture that you should have in mind. But now we don't want to just make predictions, we want to be able to make some decisions, select some actions. So what we're going to do is augment our Markov process with some actions, and then we need to quantify how good are those actions, so we're going to add as well some rewards. So here in this graph, I'm using some standard notation where circles correspond to random variables, rectangles correspond to decisions or actions, and then diamonds correspond to utilities or rewards. Okay, so in decision theory, this would be the standard notation. And now the arcs simply indicate dependencies. So again, we have that a state depends on a previous state, but now what I've added to this is that the state will depend as well on the action that is selected at each time step. Okay, because here again we don't want to just make predictions, but we want to select some actions that are going to influence future states in a good way. Right? So that's why now we've got this dependency on actions. And then the choice of actions is going to depend on the state, the current state, because the state will describe the environment, it will describe the world, it will describe, in theory, everything that matters so that we can make the best decision. We're also going to have rewards that depend on the current state and action, and the idea is that this quantifies how good it is to be in a certain state and also to execute a certain action. Okay, so this is how this model works, and now we're going to see how we can design some algorithms to choose actions in order to maximize the rewards. Okay, so before we delve into the details of those algorithms, let's make a few assumptions. Again, here we're going ahead with the idea that the process is stochastic, so it's not necessarily deterministic, so there's some uncertainty and we're going to capture this. The process is sequential, so the actions that we select are one after the other and then they depend on each other. Now, there's some additional assumptions here that are a bit restrictive. This is simply because we're just starting, this is the second lecture of the course, but then we're going to relax those assumptions as we go. But for now, we're going to assume that the states are fully observable. So in practice, let's say you've got a robot, it has some sensors, and then it will observe the state of the environment, but maybe not completely, right? And it might not be accurate. So the state might be partially observable, and it might also be, at least the sensor measurements might be noisy. But for now, we're going to assume that we can observe the state of the environment completely and exactly. We're also going to assume for now that the model that we have, which is this here, is completely specified. So we're going to assume that we know what the transition dynamics are, as well as the reward function. So that means here, at some level, we don't need to do reinforcement learning, but we're going to relax this in the coming lectures. So reinforcement learning, in fact, deals with the problem where you don't have a complete model. So in most applications in practice, in fact, you don't have a complete model simply because that would require a lot of information, and then so you need to start making some decisions and then perhaps learn as you go. And this is where reinforcement learning becomes really interesting and exciting. But okay, for now, we're going to assume a complete model and work with this. And then finally, we're going to assume as well that all the variables in our model are discrete. So that means that the states and the actions are discrete, but we're also going to relax this later in the course where we're going to consider continuous variables, so continuous state spaces and continuous actions or control. Okay, so again, we're just starting simple, and then we'll see how this works. Okay, so in our model, so we've already talked about a stochastic process which gives us the transition dynamics, but then the other important part of the model now that we've added are the rewards. So what are the rewards? So here a reward is just going to be a real number. So it can be positive, it can be negative, and then the idea is that we're going to try to maximize the reward. So the reward is essentially a numerical signal that will tell us how good the state and the action is at every time step. Now that reward, we're going to assume that it comes from a function, that the environment implicitly has a function that it uses to produce that reward. In some situations, it will be pretty clear, like let's say we're in computational finance, then the reward might simply be the profits, so the amount of money that you earn based on the decisions that you make. And then in some other scenarios, it might not be so obvious, like in conversational agents, then often you want to entertain users or you want to complete some task, and there we're going to have to come up with some numerical signals that capture perhaps some desirable properties. But in general, the idea is that with this, now we're going to be able to design algorithms that will simply maximize the reward. Another common assumption that is made is that the reward function is also stationary. And again, here stationary means that it doesn't change with time. So we're going to have the same function that is applied at every time step to produce some reward. Okay, so here the function is the same at every time step. However, it does not mean that the actual reward is the same at every time step, right? It's just the function itself that's the same at every time step. Now there's one exception. So whenever we've got some tasks that have a finite horizon, often at the end of the task, so at the last step, then we're going to have a terminal reward function that might be different from other, from the reward function at other time steps. So like if we're doing reinforcement learning in the context of a game, you might have some rewards at every time step for taking different actions in the game, but then at the very end, you might have a reward that indicates whether you win or lose. So it would be typical, in fact, to have 0 reward at every turn, and then +1 or -1 to indicate whether you win or lose, and that's only at the end of the game. Okay, so based on this, in any case, our goal is going to be to now come up with some algorithms to select actions that will maximize the sum of the rewards, and yeah, so that's our primary objective. Any questions regarding this? Yes?
So all the uncertainty is captured in this state. So this function is, there's no uncertainty in what the reward is in the state.
Okay, good. Yeah, good point. So here in terms of uncertainty, so yeah, we talked about uncertainty in the process. So the process is stochastic, so therefore the states, there's some uncertainty there. The rewards as well, here, okay, I'm actually assuming that the reward function is deterministic when I write this, but there's a more general formulation where this would also be a distribution. So when you're in a certain state and action pair, then the reward that is earned might be stochastic as well. Okay? The reason why it's common to, in fact, just assume it's deterministic is because often when it is stochastic, we'll simply care about taking the expectation, and then the expectation can be thought as a function that's deterministic again. But yeah, you're right that here it would be more general to consider stochastic rewards too. Okay, and I think there was someone else who had a question. Yes?
So in the game, 0 rewards, so it means like it doesn't change anything during the game, it's just the last step that matters?
Yeah, so in this particular example, that's right. So it would be a game where you don't earn any reward at every step, right? And it is just at the very end that you have one final reward for winning or losing. So, for instance, if you play Go, that is one way to model the game. Another way could be to say, well, each time that you play a stone, if you capture some other stones, then you could win some points for this. And then also if some of your stones are being captured, then you could lose some points for that. So we could have a different type of reward function that would reflect this. But then at the end of the day, what you care about is winning, right? And then the number of points by which you win might not be so important. So it depends on whether you're trying to define a reward function that would really try to maximize the number of points, or do you care about just winning?
So when during the game it's always 0, how does it affect the actions?
Yeah, very good question. Yeah, so if it is always 0 at every step, then you might say, like, there's no way we can learn from this, and we don't even know if we're taking good actions. But then the beauty of reinforcement learning, what we're going to see is that here we do not assume that the rewards tell us anything specific about the last action per se, but then they simply tell us something about the whole sequence of actions that happened before. Okay, so there's an important credit assignment problem here, but we're not going to assume that the last reward only tells us about the last action. So it actually tells us about everything that happened up until that point. And it's from that perspective that it is fine to just have a final reward at the end because it tells us about the entire sequence. Yeah. Okay. All right, so now I said that the goal is going to be to maximize the sum of the rewards, but perhaps an immediate reaction you might have is, well, if I have a really long process, perhaps an infinite process, that sum won't it just become infinite if my rewards are always positive? So that is a problem indeed. And then there are two solutions that are typically considered in the literature. The first one is to consider discounted rewards. So here, I'm going to introduce a discount factor gamma. That's a number between 0 and 1. And the idea is that I'm going to discount by this factor gamma the rewards that I get at every time step. So here, at the first time step, when t is equal to 1, I discount by simply gamma. When t is equal to 2, I'm going to discount by gamma square. And so on. So rewards that are earned later into the future are going to be discounted more. And then the intuition here is that we can think of gamma as really just being some sort of inflation rate, right? So if you make $10 today, right, it's worth something. But if you make $10 10 years from now, right, you're unlikely to be able to buy the same meal in a restaurant with that $10 in 10 years compared to today because of inflation, right? So then the value of that $10 is reduced due to inflation. And then so here we can think of gamma as like making explicit this idea that future rewards are going to be naturally discounted due to inflation. So in settings like in computational finance or in operations research where the rewards do correspond to money and then it's a process over a long period of time, then this is perfectly reasonable. Now the truth is that in practice, when you do this, it has the advantage as well that when you take the sum with the discount, the sum is going to be finite, okay? Because this is a geometric sum, and therefore will converge to a finite number. And so even if there's no notion of inflation, even if really there's no reason for you to discount future rewards, often computationally, it will be okay to introduce a discount factor. Now you can choose your discount factor to be really close to 1 so that it is discounting just a tiny bit, right? And then it will have the effect of making that sum finite, and computationally everything's going to be fine. Okay, so that's the first solution. The second one is you might say, well, I don't want a discount if there's no discount really in my setting, right? So there's lots of problems where really earning some reward 100,000 steps into the future is the same as earning some reward now. So in that case, really, you don't want a discount. And then so an alternative would be to consider average rewards. So here, even if we have some process that's infinite, we can take the average of an infinite set of rewards. The trouble is that computationally it's going to be more complicated. So now for the purpose of this course, we're not going to go into the details of working with average reward Markov decision processes, but there is a large literature, especially in operations research, and then there's lots of very good solutions. It's just that it's more complex mathematically. Yes?
If gamma is equal to 1, you would have the same problem, right?
Right, so yeah, so if gamma is equal to 1, it means here that we are not discounting. So okay, I guess here I said that, yeah, we would choose a discount factor that's between 0 and 1, and here I wrote less than or equal to 1, so that suggests we can choose 1, okay? The problem is if we choose 1, then yeah, we're not discounting, and this will not be finite, okay? So I mean, this would be okay if you have just a finite horizon, and then it would actually correspond to then perhaps doing average rewards. Yeah. Okay, so formally, a Markov decision process has the following components. So we have a set of states. There's also a set of actions. And then there's a transition model that corresponds to the stochastic process that we talked about. Now here the main difference is that I'm inserting this action. Right? So before it was just a probability of S prime given S. Now it's a probability of ST given ST minus 1 and AT minus 1. Right? We're just taking into account the action. We have a reward model. That's our reward function. There's also a discount factor. And then finally, there's a horizon, H, that indicates how many time steps are we planning for. And here, H could be finite. It could also be infinite. And then finally, the goal here is going to be to find an optimal policy. So in other words, a mapping from states to actions. Okay, so just to make things concrete, let's look at an example. This is from operations research. Yes, a question.
Sorry, I just want to make sure about the horizon. Does that mean that does it correspond to the equation that we're trying to maximize? That in the previous slide is we try to maximize the sum of rewards, and does that H count as the next H steps that we're trying to maximize?
That's right. So here, when I wrote sum of rewards, I was being casual, and I did not include any upper bound, but here H would be the upper bound for T. Yeah. Okay, so yeah, so here's a concrete example in terms of inventory management. So in this example, you imagine that you have a warehouse, and then there's a retail shop attached to it, and then you're selling some widgets, and then there are customers coming in every once in a while and buying some of your widgets. So now here the problem is you need to decide when you're going to order more widgets from your suppliers and then perhaps store them into your warehouse. And here the trade-off is that if you don't have enough stock into your warehouse, at some point you might have a day where lots of customers come in, you run out of stock, and you lose some sales, right? Or the alternative is you say, all right, I'm going to make sure that I always have enough stock, so I'm going to have a large warehouse, and then I'm going to always have a good supply, so I never run out. But then I will have more costs because I have to essentially heat that warehouse and then build it. And so there's more costs associated with having a large warehouse. So then the question becomes now, how should we go about ordering those widgets so that we perhaps increase the sale as much as possible, so we never miss any sale, but at the same time, we don't pay too much in terms of cost with respect to stocking all those widgets. Okay, so at any point in time, the state is going to be the inventory levels of all the different types of widgets in our warehouse. We're going to have two actions that can be, let's say that every day we get to place an order if we want. So either we don't place any order, so we do nothing, or we place an order, and then this order could include a different quantity for every type of widget. Okay. Then there's also a transition model that will tell us how the inventory levels change over time. This will depend on the demand from the customers. And here, we don't really know how many customers are going to show up on a daily basis, right? So it's typical to then assume that we have a stochastic demand. And there are various models in operations research that are used for this. And then even if we don't have a model, we're going to see later in the course that through reinforcement learning, we can get some algorithms that will essentially learn over time what might be that demand and then make some decisions based on that. But essentially, the demand here would be a conditional distribution over the next inventory level given the current inventory level as well as the orders that we put in. And it's stochastic because we know what is our current inventory level, we know what action, so whether we are ordering more widgets, but we don't know if some customers are going to come in and how much they're going to buy, right? So that's why the transition is stochastic because of this uncertainty with respect to the demand. And then the reward model here could simply be the sales minus the cost minus the storage. So all the widgets that we sell, we earn some money. Then we had to buy them in the first place, so there's some cost associated with that. And then if they have been stored into the warehouse for some time, then there's some storage costs associated. Okay, and then finally, we can have a discount factor. So here, I chose 0.999. It's something close to 1. Perhaps here we do care about inflation, but I mean, the inflation rate these days is very low. And then this might be a process where at every day we get to place a new order. So really the inflation on a daily basis is tiny. And then so here, I'm not sure if this is realistic, but in any case, this is just as an example, we can pick 0.999. Okay, and then finally, for this problem, we would like our business to keep on going forever, right? So we don't want to go bankrupt anytime. So really, the horizon should be infinite. Okay, so, and finally, the goal now is to come up with a policy. And then what we really want is to make sure that we come up with the right trade-off between increasing supplies to make sure that we don't lose any sale, and then at the same time decreasing the storage cost because that is affecting as well the profits. Yes?
So here in this example, in the order widget action, we don't specify how many widgets we want to order, just some fixed amount.
Right, so okay, here I guess I simplified the example. So normally we would also indicate a quantity for each widget. So there would be more than just two actions. You could imagine that for every level of order, like maybe with your supplier, you can order widgets in quantities that are, I don't know, multiples of 1,000, right? So for every level like this could be considered a different action.
It could even be continuous.
Yes, so it could also be continuous. So okay, in this example, it's discrete, but now let's say that it's a problem in robotics where you have a control and then so you essentially apply a force. Then really this would be something that's analog and therefore continuous. Internally, it might be digitized and therefore discrete, but it is helpful to think of it as continuous. And then in computational finance, you might have an action that's like buy some stock at a certain price or sell at a certain price. So there too, the price, you can think of it as continuous, even though it's usually discrete because it might be rounded to each cent. But yeah, it will be useful to think of it as being continuous. Okay. Good. So Next, we need to describe how we're going to select actions. And so we're going to formalize this by defining a policy. So here a policy is going to be denoted by pi. And then it takes as input the current state. And then it produces an action. So the goal here in Markov decision processes, as well as reinforcement learning, is essentially to come up with this policy pi. So it's really like a lot of what we're going to talk about in this course is really how can we find this function, how can we optimize it, and in order to maximize the rewards. Okay, so again, I'm making the assumption here that the states are fully observable. So as a result, I can simply condition my choice of action on the current state. So if my process is Markovian and it is stationary and also the states are fully observable, then here we can argue that the state of the environment contains all the information that matters, and we don't need to look at previous states. All the information that matters is captured in the current state, and then I can simply condition my choice of action on that state. Okay, so we're now ready to talk about how we're going to evaluate and optimize policies. So let's say that I come up with a policy, so I have a function, and now I'd like to evaluate how good it is. So with what we defined now, to be more precise, so earlier I said that it's going to be the sum of the rewards, but the reality is that those rewards depend on which state we end up in, and then the states themselves, there's a stochastic process. So here we take that into account by really looking at the expectation of the future states, and then I'm going to also discount the rewards by this factor gamma. Okay, so this is the objective that we're going to work with in this course. So this is the discounted cumulative rewards, where I have a sum with respect to all the time steps from 0 to h. So h is our horizon. And then this is the reward at each time step. It depends on the current state, but that state, there's some uncertainty. It really depends on the transition dynamics that are stochastic. And therefore, here we're going to have an expectation. Okay, so that's the objective. That's what we're going to use here to evaluate a policy. So this expression, I'm going to say that it corresponds to the value of the policy pi when we start in state S0. Okay, so this is the value of one policy. Now, what I want to do is come up with the best policy, so the one that has the highest expected utility, and I'm going to denote this best policy by pi star. So here the star indicates that it's the optimal policy. Now, in terms of optimizing policies, there's lots of algorithms. In this course, we're going to talk about value iteration, policy iteration, as well as search techniques. This is for still, again, classic Markov decision processes where the model is known. Then when we get into reinforcement learning, we will see that there are various algorithms that are variants of value iteration, policy iteration, and search techniques. There's also linear programming, but we don't have time to cover everything, so I'm going to skip that one, and we'll focus mostly on those three. Okay, and then in general, the computation to find a good policy, that can be done offline before we start the process, so essentially planning ahead, or it can be done online as we go, as we execute our policy. So it could be, as an example, it's a bit like if you play a game, you could say, I'm going to plan ahead and then decide all the moves I'm going to make as before I start the game. Or you could say, as I play the game, depending on how the game evolves, I'm going to recompute or adjust my policy and do some more planning. Okay, so we're going to see those two types as well. Yes? Right, so here we start in S0, right? And now t steps into the future, we're going to be in ST, right? And we need to know what is going to be ST in order to compute the reward, right? So that's why there's a reward associated with every time step. It depends on ST, but I don't know what is ST, so I'm going to have here an expectation. And actually, right, so I guess here I am missing a sum with respect to ST. Yeah, I guess I am missing a sum with respect to all the STs in this slide. Okay, so I will fix this. Yeah. Yes?
Or is independent of the initial state or the previous state probability and the probability distribution?
Right, so okay, earlier we talked about a stochastic process where the current state just depends on a previous state. But now I don't know what the previous state is, so I could look again at my conditional distribution and see that that previous state depends on the earlier state again, and then I would keep doing this until I reach the first state S naught, right? So here, instead of writing all of this down, I just compress that to the probability of ST given S naught. Oops, okay, so let's now talk about a first algorithm known as value iteration for optimizing policies. And so we've got again our Markov decision process. And then the way this algorithm is going to work is essentially backwards. It's going to optimize actions, select actions going back in time. And here the intuition is a bit like when you're planning and you're going on a trip. Let's say you need to go to the airport because you want to catch a flight, and then so you're planning your day, and then you know that your flight is, let's say, at 3 p.m. So then you need to work back and say, I need to be at the airport at 1 p.m. In order to get to the airport at 1 p.m., I need to get a taxi perhaps an hour before that. And then before that, then I need to be completely ready, so I might have to eat and so on. So you kind of work back in time. And so it's a natural way of doing things. And then here we can show that in terms of algorithms, to find what is the best action at every step, to find a good policy, we can use dynamic programming that will work backwards and optimize the last decision, then the second last decision, and so on. Okay, so here's how value iteration works mathematically. So we start with the last decision. So we're at the last time step H. And at this last time step, this is essentially our last action that we're going to be able to execute. So here, the value or the rewards that we can get at that last time step is just R of SH AH. Okay? So now if we want to optimize what is that last decision, then it's easy. We simply look at all the possible action and choose the one that gives us the highest reward. Okay, so the last decision is easy because it's the last one. There's nothing else to worry about. Then after this, we go back one step and now ask what would be the second last decision that would be optimal. And now we want to take into account the reward for the second last time step as well as the last time step. And here we're going to sum the rewards, right? So we have the second last reward plus the discount factor. Then after this, I have an expectation with respect to what will be the last state, SH, given SH minus 1, and times the value that I can earn in that last state. So this corresponds, again, to taking the sum of the rewards in the last two time steps. And now I'm going to simply select AH minus 1 to maximize this, where I already have V of SH, where I've already optimized AH. Okay. So this is with one time step, but then we can continue with two time steps. Then we have a similar expression. So we're going to look at the reward for two time steps left plus now an expectation with respect to the state that I can reach times the value for the remaining steps. And then the value for the remaining steps, you see, would be the value at SH minus 1, and that was computed up here. So you can see here that this is a form of dynamic programming because for every time step, I compute a value for each state, and then I store this. Then, so this is the last time step, then I go back one step, and then I add the rewards and optimize immediately what would be the corresponding action. Then continue, 2 time steps left, I optimize again, and so on. Now, if we do this for the entire planning horizon, we can see that this generalizes to what is known as Bellman's equation. So this is a very important equation for Markov decision processes and reinforcement learning, where you can relate the value for 2 consecutive time steps, and then the equation is essentially the same as those 2. And now here, instead of referring to specific time steps, I've just put t, meaning that this will hold for any time step. Right? So the value at time step t for st is going to be the max with respect to the possible actions of the current reward plus the discount factor times an expectation with respect to the following state, and then we take the value in that following state.
What if
Yeah.
horizon is infinite? Because h appears in that formula.
Yeah, okay, very good question. Yeah, because if the horizon is infinite, we've got a problem, right? We can't do this infinitely with an infinite number of steps. So we're going to have to make some approximation, and we'll get to this in a moment. Okay. All right, so this equation was to compute the value, but now you might ask, what's the equation or what's the mathematical formula to get the optimal action, to construct the optimal policy, right? So the policy is a mapping from states to actions, and now if I'm in state ST, right, then what I'd like to do is find what is the best action, and here I essentially have the same expression. The difference is that instead of returning the value that is maximal, I want to return the argument. So here argmax means the argument. So in other words, I want to return which action led to this highest value here. Okay, so finding the optimal action is really the same as finding the optimal value. It's just that we return the argument instead of the value. And again, argmax stands for the argument that maximizes the value. Okay, so let's look at a concrete example. So here, it's a little scenario where perhaps you have a company, okay? And then if you look at companies, they go through different stages. A company, would start being a startup, and then when it's a startup, perhaps it's poor and unknown. Okay, so if it's a startup, it might not have a lot of money, does not have much resources, and it's also unknown because it just started. Okay, so this could be one state. Then after some time, the company might have some products that are interesting, and then it might do some advertising, and then the company might become famous. Okay, so some startups very quickly become famous, right? But then in some cases, they're still poor. Okay, so this is a state where the company is poor but famous. Now, some companies take a different route, and then in their case, the products might not be known by the public. It might be more a B2B type business, and then the company might be very successful, so it's rich, but it's unknown. Okay, so some companies are of this type. And then eventually, some companies might become both rich and famous. So their products are well known, and then they're also selling very well. So both rich and famous. So now the question is, depending what state the company is in, what should it do? Okay, so here we have 2 possible actions. The company might decide to just save its money, or it might decide to advertise. Right? So you want to advertise to drive the sales, but at some point, once the sales are going well, maybe you can stop advertising and you can just save your money. Okay? So at any point in time, you can choose between save and advertise. Now, depending which state you're in, like you see here, if you advertise, there's some probability 0.5 that the advertising is not going to be successful and it's just going to fail, and then the company is going to remain unknown. Okay? But there's a probability that the advertising will be successful and now the company is going to become famous. Okay? So in this little scenario, you see the transition dynamics are such that we go from this state to that state with a probability 0.5, or we could stay in the current state with probability 0.5. If the company decides to save, so here the company will obviously remain unknown, and well, in this case it was poor, so it will also remain poor, so the probability will be 1. So you can see all the transition dynamics that are indicated by the arcs and all the probabilities that are associated with each arc. Okay, and now there's a reward associated with each state. So if a company is poor and unknown, we'll say that this is a reward of 0. If it's poor and famous, same thing. But once it becomes rich, perhaps this is good. Let's say you're a shareholder, so you want your company to become rich. So then plus 10, and same thing here, plus 10. Okay? So this is obviously a simplified example, but interesting that will illustrate how this works. Okay, so now the question is, in each state, what should the company do? Right? And then the goal is over time to earn as much reward as possible. And then those rewards, right, are those numbers. And then so ideally you want to be in some states where you get this plus 10, right? So you want to get rich. Okay, so with this example, we can run value iteration as I described it. And in this table, I'm showing the values that are found for every state as we do value iteration starting from the end. So starting from time step H and then going back in time. So at the last time step, if you recall, the equation to compute the value is just the max of the rewards. Okay, so here we're going to take the max of the rewards. So if I am in this state, poor and unknown, whether I save or advertise, the reward is the same, and it's going to be 0. Okay, and then it's the same thing for all the other states. And if we look at the policy, same thing as well. So here we would take the argmax instead, and because it doesn't matter whether we save or advertise, then we're going to get 2 actions that are optimal, so advertise and save. Okay, just to be sure that we're all on the same page, let me write down the computation here on the board that would correspond to doing this. Okay, so here, if I take as an example the last state, so rich and famous, and I'm going to show you how to compute the first 3 values. Okay, so we want to compute VH of RF. Okay, and in this case, according to the equation that we saw, so it's going to be the max of 2 possible rewards. So R of RF and action A versus R of RF and action S. Okay, and then both of them give us 10. So therefore, this is equal to 10. Okay, so this value here is equal to 10. Now, if we look at the policy, so pi of RF, this is again at time step H, it's equal to the argmax of RF A versus RF S. And then so here the argmax is with respect to the actions, and then we saw that is the same. So in this case, we have two possible actions that are optimal, so both A and S. Okay, so that's why we have this here. Okay, now if we go one step back, so H minus 1, let's see how we obtain 19. So if we consider VH minus 1 of RF, that's going to be the max over actions of RF actions plus gamma sum over the state, then probability over the state given RF and the action times VH of the state. Okay, so for this value, this is what we would compute. And then in this particular example, it would correspond to taking the max with respect to 10 plus 0.9 times 1 times 0. This is for the action advertise, I believe. Is that correct? Yes, so if we advertise, we've got a probability of 1 of reaching poor and famous. So that's why we've got here a probability of 1. And then poor and famous has a value of 0. Or we could also have the save action, so 10 plus 0.9 times 0.5 times 10 plus 0.5 times 10. Okay, and then this one is for save. And now if we compare these values, this one gives us 10, and the second one gives us 19. So therefore, 19 is the highest value. Okay? And then pi of H minus 1 RF. So what's the optimal action one step back in the state rich and famous? It will be the action that led to the highest value, which is save. Okay, and that's why here we've got save. Any questions regarding this? Yes?
In the VH, you have reward of RF, comma H,
In VH, yes?
yeah, the first one, should that be 0? Or RF, comma A. So the advertise to go back to Boolean.
So okay, here, this is the reward when we're here. And then whether we advertise or save, the reward is plus 10. Okay, so that's why we've got 10 for both actions. So this is a simplified scenario where the action has no impact on the immediate reward. Yeah.
So in this table, we don't really care about exact values of a value function, right? We only care about relative values across the row.
Yeah, so yeah, the question is whether we care about the relative or the absolute values of the rewards. So at some level, in order to make decisions, yeah, we just care about the relative magnitude of those rewards. However, in a specific domain, you might care about the absolute values because the absolute value might mean something. So like in this case, if this corresponds to profit, you want to know how much profit you're going to earn, and therefore the absolute values or the exact values do matter.
Because they keep increasing as H decreases.
So here the values keep on increasing, and this reflects the fact that perhaps at every time step, right? So this could be like 1 year, right? And maybe this 10 could correspond that you made $10 million in profit, right? And now, so this would mean that in year 1 we make $10 million. After 2 years, the sum of all the profits would be $19 million. After 3 years, 25 million, and so on. Okay. Let's keep going. All right, so what I did here is explain how we can do value iteration. And then when h is finite, there's something interesting because the policy is not going to be stationary. So here again, stationary means that it would be the same at every time step. So here, if I go back, you see the policy, right? It changes depending on which time step I'm looking at. So here, if I'm in the state RF, at the last time step, I would choose either A or S, but then all the other steps after this, in this particular example, I would choose S. And then there's something similar going on. So for every state, right, then the policy might change depending on the time. So this is a little counterintuitive because we defined our problem to have some transition dynamics and some reward model that are stationary. So how come here we have a policy that is not stationary? Yes?
In this slide, so why phi of h for when we are in RF, when we do advertise is 10? Because if we do advertise, we go to Pn, which is 0, right?
Mm-hmm.
This one in second, so V of RF is 10 here, right? So why is it 10? Because if I take A, I go to Pn, and the reward there is 0.
Yes, okay, so here at the last time step, the reason why it's just 10 is because we execute an action and then it's over. We don't transition further, we don't earn any more rewards. Okay, because you're absolutely right that at that last time step, if I advertise, I'm going to go to a state here where I earn 0, and then if I save, then there's a chance I'm going, well, in fact, if I save, I end up either here or here. In both cases, it's 10. But at that last time step, what we're saying is that it's over. This is like last chance, and then after that, the business closes. Okay, so it's last chance to execute some action and earn some profit. Okay, so in that case, it doesn't matter because there's no more transition. This is the last time step. So in the case, I mean, for this problem, it's a little bit weird because with a business, you don't want your business to close, right? But I'm just illustrating for a finite horizon problem, right? Then this would be the last time step, and therefore there's no more transition. So we just look at the reward that's earned immediately.
So meaning whatever action we do, basically we still are in RF state?
Whatever action we do, it's over. We're not in any further states after that. It's over. That's what it means. Okay, maybe a better example would be a game. Okay, let's say that you're playing a game. Maybe let's say let's consider hockey. Right? There's a time limit. Right? The game's going to end at a certain point in time. Right? And then you might be like one fraction of a second before the end of the game, and then you just hit the puck. Right? It's going towards the goal. Now, the game is over, the puck enters the goal after. What does that mean? No goal, because it's over, right?
In the example you said, there is no reward, right? It's nothing, but here you're getting 10.
Yeah, so you're getting 10 for the current state, but you're not getting any further rewards for any future states you're going to reach because it's over. It's at H, it's the process terminates.
So then there's no difference between like, it's being over or you actually getting 10.
Yeah, so the current state gives us 10, and then after that there's no more transition. So it would be a case where there's no arc because the effect of choosing an action, right, would not lead us to any further states. So we get the 10 for the current state, but that's it. Yeah. Yes?
So in this model, like in the previous graph, we have an agent that selects an action, and then the reward will depend on the action and also the state, right? And in this example, the reward just doesn't, because the reward is correspond to the current state. So, so one problem I have is, which one will we prefer? Like, why would we choose like over? We define on the current state, or we define on like the state and then the action combined together?
Right, okay, yeah. So the question is about, do we define rewards to be just with respect to states or state and action pair? So the most general is to consider state action pairs. Okay, so So here perhaps I should have given you an example as well where the action leads to a cost or leads to a reward as well, and then we would see that there would be a different reward depending on which action is chosen. So this is just, a simpler problem. Yeah. Okay. All right, so as we just saw, the policy is not stationary, and then here it has to do with the fact that the problem has a finite horizon. So the best action that you're going to choose depends on what is the time step, and intuition is that if we have no more time left, then we don't have to worry about the long-term effect of the action. We can choose an action that will just allow us to maximize current reward. But if we have more time left, then we need to choose actions that will maximize the current reward as well as future rewards. Right? So if I just go back this equation here, right? So you see when there's no time left, I choose an action just to maximize this. When there's more time left, then the equation is different. Right? So I choose an action to maximize the current reward plus the expectation of the future reward. So it's normal that as a result, I would get a different policy depending on how much time is left. And intuitively, we can observe this in many scenarios. So again, if you play a game, let's say hockey, right? So near the end of the game, the players are going to play differently than throughout the game, because near the end, they might do everything they can to try to score in order to catch up. Right? Whereas throughout the game otherwise, they might play more conservatively because there's a risk that if they are trying to attack too much, they might, create some opening, and instead the opposite might happen where they might get scored against. Right? So in games, we can observe this. So players typically play differently at the end versus throughout the game. And so same thing here. Okay, now, if we have an infinite horizon, what we're going to see is that the policy can be stationary. So there exists an optimal policy that is stationary, meaning that we can have the same mapping at every time step. The intuition for this is that here, there's in fact the same amount of time left, regardless of which time step we're at, because the horizon is infinite. So there's always an infinite amount of time left. So even if you take more steps, right, then there's still an infinite amount of time left, so there's no reason for you to behave differently. And then we can show that there exists some policy that is optimal and stationary. Okay, the main problem with an infinite horizon is that value iteration would have to do an infinite number of iterations, and we can't do that. Okay, so we're going to see in the next set of slides how to deal with this. So the intuition, before I show you formally, is that even though we should be doing an infinite number of steps, if we do a finite number of iterations, then we're discounting at every step by the factor gamma. So if I do n steps of value iteration, so I'm going to add up rewards, and then the last reward is going to be discounted by the factor gamma to the n. Now, depending on what gamma is and depending on what n is, well, gamma to the n will get smaller and smaller, and eventually it will converge to 0. It will approach 0. So if you take n to be large enough, then those rewards that are like way into the future become negligible. So here this gives us a way to say that, or at least it gives us a way to approximate this infinite process where we can say, let's just do value iteration for a finite number of steps, stop, and as long as that number of steps is large enough, then the rewards that we're not taking into account beyond that, they would get discounted so much that it's negligible, and then maybe it doesn't matter.